let's review over the graphs of sine and cosine. Yesterday, began looking at that. We're going to spend really the next several lessons looking at different aspects of the graphs of the sine curve and the cosine curve. Let's talk about f of x equals the sine of x. Get some graph paper out as well. You want to have that for the next several lessons. Oh! As I throw the graph grid at myself. Let's try not dying. Right, Ethan? Yeah.
Why?
Oh, just because of yesterday.
Yesterday.
The ditch.
Oh. Oh, it's a lot.
Am I going to need more than one equation?
I don't know. All right, and so on your graph grid, remember we said we don't need to really make the f of x axis very tall, but we'll need a fairly lengthy positive x-axis. And we said we're going to let every how many boxes equal 1, class?
2.
Every 2 boxes is going to equal 1. So we have 2 boxes to 1, 2 boxes to 2, down 2 boxes to -1. If you have room, down 2 boxes to -2. But we're not going to label 1, 2, 3, 4, 5 on the x-axis, though technically those increments would still be correct. Instead, we're going to label our quadrantals. But we have to use what units? Radians. And it's okay to think degrees, but we actually have to label radians. So for instance, if we go over 3 boxes, we would think 90 degrees, but I'm going to write pi over 2, because pi over 2 is about 1.5. It's 1.57, so it's a little bigger than 1.5. But we're going to put it at 1.5, which would be 3 boxes. Then at 6 boxes total would be 3. But now we're going to go a little bigger than 3, but we're going to put it there anyway and put pi, which is a little bigger than 3, right? 3.14. 3 more boxes, we'll put 3 pi over 2. And then finally, 3 more boxes, we'll put
2 pi.
And by the time we're done with the entire 2 pi, we'll be about half of a box off, which is about 1/4 off. That's not significant enough in my mind to make it worth the hassle of being that tiny bit off. So we're just going to graph it like this. And we said for f of x equals sine of x, the best thing perhaps to do is to remember the unit circle. Or we could memorize key points. And you should have in your notes the key points for the sine curve. What are those 5 key points on the sine curve, anyone?
0, 0.5, 0.7.
Nope, just the key points. I told you to write 5 key points.
0, 1, 0, -1, 0.
Good. We're going to track the sign as it goes throughout the progression. Your key points are 0, 1, 0, -1, 0. Say those with me, class. 0, 1, 0, -1, 0. So we're going to start at 0, 0. But then at the next quadrantal, we're up at 1. The next quadrantal, we're going to be at 0. The next quadrantal, we're down at -1. And then at 2 pi, we're back to 0. Those are your key points. Now, it wouldn't hurt to memorize that right near the 1s are your square root of 3 over 2s, or your 0.9s, or your negative 0.9s. It also wouldn't hurt to memorize that near the 0s are your 1/2s, or in the 3rd and 4th quadrants, the negative 1/2s, which is 1 box. And if you plot those points there on your graph grid, we can connect them with a smooth, continuous curve. We don't want any straight lines. If you remember graphing parabolas back in Algebra 2, nice, smooth curve. And there we have f of x equals the sine of x. Now, of course, that's not the entire curve, but you really can't graph the entire curve, can you? Because we said it's just going to keep going and keep going all the way to and beyond. And the other way, it's going to keep going backward to negative infinity. So we said that the domain of f of x equals the sine of x is all real numbers, negative infinity to infinity, or we could just say all real numbers. But the range, you can even see it in the key points. The sine curve is never going to go lower than -1, nor higher than 1. So the range, your f of x value, is always between -1 and 1. It does hit the -1, it does hit the 1, so it's in brackets, but always stays between those values. And there was another term I gave you to describe how long it takes along the x-axis to complete a full cycle. Well, obviously we can see it takes until 2 pi to complete the cycle. We said it would finish another cycle by the time we got to 4 pi and so forth. What's that term that describes the length along the x-axis to finish one cycle of the curve class?
Period.
The period of the curve, and of course then obviously the period of the sine curve is
2 pi.
2 pi. All right, so several things to note here. One other thing, you can't see symmetry when you only graph one period. But if I were to go backward, you could see the period here. What is sine symmetric to? Does it reflect across the y-axis? No. Does it reflect across the origin? Yes. So because it's got origin symmetry, that's evidence that sine is an odd function. Of course, we already remembered that from previous lessons, right? That f of negative x would be the negative of sine x. We looked at that last lesson, but it just helps to see graphically the fact that sine is odd. So a lot of the things we talked about the domain of sine, the range of sine, the even oddness of sine and cosine, and we can see it graphically here. Questions on this graph? Let's take a look now, if you would, at the cosine of x. F of x equals the cosine of x. And I'm going to be lazy, and I'm going to get out a different color of chalk here. And we're just going to do that rather than redraw a graph. Or maybe you switch to pen, for instance. Could work for you.
I used that because it's hard to see pencil.
Already used the pen. All right. Maybe use a different color of ink. I don't know. All right, so let's go with yellow here. And say f of x is equal to the cosine of x. We need to have memorized the key points of the cosine curve.
1, 0, negative 1, 0, 1.
Good, you probably don't have them memorized yet, and that's fine, but we need to know that they're 1, 0, negative 1, 0, 1. Say those with me, class, for cosine. 1, 0, negative 1, 0, 1. Now let's go and graph these at the quadrantal. I'll use x's to help this show up a little better as well. So we're starting at 1, then to the next quadrantal 0, then down to negative 1, back to 0, back to 1. And if that's all you plotted, you'd probably make a straight line V, but of course we know it's not going to make a V. It might help if we remember that near the 1s we have 0.9, well 0.86, square root of 3 over 2, but close enough, right? So right here after the 1, and right here before the 1, and then down here on either side of the negative 1. And then near the 0s we have 0.5s, just like we did on the sine curve. Well, in this case, there's going to be one above and one below, and one below, and one above. And if we were to connect these points with a smooth, continuous curve, we'll get our cosine curve. Now, what's interesting is if I were to complete this, if I were to keep going, and keep going. I want to direct your attention right here. What does this look like if I just went from here to here, class? That's the sine curve, isn't it? But it shifted back 90 degrees, complementary to the sine. Does that make sense? We're 90 degree shift, and sine and cosine would be equal because sine and cosine are 90 degrees apart, aren't they? They're complementary functions. So it makes sense that the curvature of the graphs really are the same. I suppose we could also come over here forward 90 degrees and you'd see the same thing. It just kind of looks like it's flipped upside down. But yeah, so the key points, 1, 0, negative 1, 0, 1. But just like the sine curve, it's going to keep going to or negative infinity. So we could say that the domain along the x-axis is all real numbers. We could also note, though, that the range, the y values, or f of x values, go no lower than negative 1, nor higher than positive 1. So like the sine curve, the range is negative 1 to 1. Furthermore, we know that the period of the curve is also 2 pi. Every 2 pi, the curve will repeat. But we also notice, looking at the yellow graph here, right? Does it mirror itself this way, side by side?
Yes.
Yeah, it does. So that means because it mirrors across the y-axis, cosine is an even function. Of course, we'd observed that in our previous lesson mathematically. And again, we see it here graphically. All of this we covered yesterday. Wanted to review it before we started into anything new. Any questions on this? All right, now here's what we're going to do over the next several lessons. We're going to take these nice basic sine and cosine curves and we're going to monkey with it. We're going to stretch it and squish it and flip it and shift it and all kinds of crazy stuff. And we're going to do it all with mathematics. Now, if you have a really good memory, you might remember back to right before COVID hit when you were in Algebra 2. And in Algebra 2, right before COVID hit, we were working with parabolas. And we did the same thing. We stretched it, we smushed it, we shifted it, we flipped it, all those things. So if you have a really good memory, you could go back in your mind to end of third quarter Algebra 2, it's going to look very similar to that.
It's like the last thing I learned.
Pretty much, yes. All right, so what we want to talk about here, the first change we want to make to the sine and cosine curves is amplitude change. So next thing in your notes, amplitude. Amplitude refers to how high or low the graph goes from the x-axis. Amplitude refers to how high or low the graph goes from the x-axis. Well, I just erased it, but you still remember what it looked like, right? How high did the sine curve go, class?
Oh, like 3 boxes?
It went up to 1, and it went down to -1. So the farthest it ever went above or below was 1, right? So we would say that the amplitude of the sine curve, the amplitude of the cosine curve is 1, and there's a reason for this. Because if you look at the function of x equals sine x, there's an understood 1 in front of the sine. If it were any other number, it would be a different amplitude. So I want you to write this in your notes under amplitude. F of x equals a sine of x, where a is the amplitude. The a value is the amplitude. Whatever number comes before the sine function is going to change the amplitude. And the best way to change the amplitude is to adjust the key points. To adjust the key points. Basically, you're going to multiply a times normal values. You're going to multiply all the normal values we would have times a. So for instance, if I had f of x equals 2 times the sine of x, we're going to take all of our normal sine and cosine values and multiply them all by, or all our sine values and multiply them all by 2. Because it's 2 times the sine of x. So we're going to take all of our normal values times 2, which means as you set up your new graph grid, instead of going up and down as far as 1 in both directions, it's going to go up and down as far as 2 in both directions. We normally have enough room for that anyway. I'm going to give myself just a tiny bit more room so I don't hit the top or bottom of the graph. But we're still leaving the x-axis just as it's always been. So normally for the sine curve, we have what key points, class?
0, 1, 0, -1, 0.
All right, good, Quentin. 0, 1, 0, -1, 0. But we're going to change it. We're going to multiply all of those by 2. So what are my key points going to be now when I multiply all of these by 2, class?
0, 2, 0, -2, 0.
There we go. So on your graph grid, we're going to start at 0. The next quadrantial is going to be a 2. The next one is 0. The next one a -2. And the next one a 0. Adjusting the key points is the first major step. But to get a nice smooth curve, we want to change some other things. Remember, right next to what used to be 1, in fact, I'm going to kind of draw this light sketch of what the old graph used to look like. Right? This was our old sketch. Right next to the 1 and the -1 class, we would be at 0.9-ish, right? Technically square root of 3 over 2. Well, if you multiply the square root of 3 over 2 times this 2, you get what?
Square root of 6.
Square root of 3, which is 1.7. Now remember, this is 1, this is 1.5, this is 2. 1.7 is going to be pretty much right in the middle. So beside it, we're going to go about halfway down the box, and over here we're going to go halfway up the box. Does that make sense? So about a half box up and down. So a little bit more pronounced drop down and push up than we had before. And remember, beside the 1, beside the zeros, we would have halves, right? But if you double a half, you get 1. So we're going to go to 1 here, and then on the other side, we're going to go down 1. Does that make sense? So we're simply taking all the values we normally use and doubling them, multiplying them all by 2. And then we connect with a smooth, continuous curve. Like that. And now that's f of x equals 2 sine x. Pretty straightforward change. Again, the key is to know what normal numbers you would use for the graph and simply double them all. But let's keep that same grid and maybe change to a different color ink or something, or maybe a pencil or a pen. What if I had f of x equals a half cosine x? Well, that means I'm going to take all my normal values for cosine and multiply them all by a half. So my normal key points for cosine class are, there we go, 1, 0, negative 1, 0, 1. But I'm going to cut them all in half. So I'm going to actually get
0.5, 0, point negative 5, 0, 0.5.
There we go, half, 0, negative half, 0, half. So we're going to start at 1/2, go to 0, down to negative half, 0, and half. And remember, we used to be right beside the 0, we'd be at a half, right, which is 1 box. Now we're only going to be at a half box on either side. And you remember how before, in fact, I think I need to maybe zoom in just a little bit here, help the YouTube audience out, including Jamie. Hi, Jamie. We miss you today.
No, we don't.
Chris, don't be salty. Jamie never hurt you. All right, and normally, remember, we drop down just a little bit. We're going to drop down even less than a little bit. Like, we're almost still going to be at that half. Almost going to be at the negative. Just barely any drop down or shift at all from that line. And then when we connect the dots, we see a smushed cosine curve. It has the same down and then back up shape to it, but it's just compressed in by an amplitude that is smaller than 1. Whereas the sine curve kept its shape, but was stretched a little bit bigger by the number bigger than 1. Does that make sense? All right, set up a new graph grid then. Let's go set up a new graph grid and do a couple more of these. Another graph grid on your graph paper. Give yourself plenty of room this time on the f of x axis. Pi over 2 pi, 3 pi over 2, 2 pi, and then 1, 2, 3, didn't quite go to 4. Negative 1, negative 2, negative 3, didn't quite get to negative 4. And let's do f of x equals 3 cosine x. F of x equals 3 cosine x. Well, what are my normal key points, class?
0,
For cosine.
Negative, or 1, 0, negative 1, 0, 1.
But I'm going to multiply all of them by 3, so instead we're going with
3, 0, negative 3, 0, 1, 3. Yep.
all right, so we're going to start all the way up at 3, all the way down to 0 for the next quadrantal, then all the way down here to negative 3 at pi. 3 pi over 2, we're back to 0, and 2 pi all the way up at 3. We're going to stretch this graph quite a bit. Do you remember stretching the parabolas?
Yeah.
It was the same exact thing. It was whatever the coefficient of the binomial squared ended up being. Now remember, normally, and I'm going to trace what we used to have for our basic cosine curve. This is what we used to see, right? Right beside the 1s were 0.9s, correct? Technically, they were square root of 3 over 2s. But we're going to multiply that by 3. On your calculator, take that square root of 3 over 2, multiply it by 3. What do we get?
2.59.
2.59. Now remember, here's 1, 2, 2.5 is just a tiniest bit higher than the 2.5. And then down here, just the highest, littlest bit below the 2.5. Does that make sense? And then remember, on either side of the zeros, we'd have the 0.5s here and 0.5s there. But we're going to multiply those 0.5s by 3 to get 1.5. So instead of 1 box up, 1.5 is 3 boxes up, 3 boxes down, 3 boxes down, 3 boxes up. So again, positive in the first and fourth quadrants, negative in the second and third quadrants. And when you draw, don't come straight down. There's going to be just a little bit of a curvature before you start dropping rapidly. And a little bit of a curvature at the end, just like there's a little bit of curvature. Because again, if you were to keep going, it would be coming down like that, right? On the ends if it kept going. So make sure you curve just a little bit there to the ends.
Remember when I used to lose all those points for not being able to draw a curve?
Yep. Welcome back.
Still can do it.
Yeah, you know, as long as you're braced for losing more. Hey, as long as the stretch is accurate, you know, you lose neatness points, but not accuracy points. Too bad. So, you know, make sure we try to be as accurate as we can be. All right, questions on this graph? Again, this was more stretched because we had a bigger amplitude. What if we had, let me change colors here.
0.2.
Oh my, do you really want to do that? I don't want to, I'm lazy. F of x equals 2.5 sine x. F of x equals 2.5 sine x. Well, normal key points.
0, 1, 0, negative 1, 0.
But we're going to multiply them all by 2.5.
0, 2.5, 0, negative 2.5, 0.
All right, so we're starting at 0. Is that on the screen? Yes, we're on the screen. 0, 2.5, 0, negative 2.5, 0. And this is where it gets really fun. I say that. Because we know that normally we're at square root of 3 over 2 up here at the 1 and square root of 3 over 2 next to the negative 1, right? But now that's going to be square root of 3 over 2 times 2.5. What's that going to be? On the calculator.
2.165.
2.16. All right, so just a little bit above the 2. So here's my 2. I'm going to go just a nudge above the 2 on either side and a nudge below the 2 on either side here. And then normally I'd be at 0.5s, right? But what is 0.5 or a half times 2.5?
1.25?
All right, yeah, I think that's right. 1.25? Yeah. The same thing? So 1 1/4. Well, here's 1 1/2. So we're going to be exactly in between the 1 and the 1 1/2 on both of these, and then in between the 1 and the 1 1/2 on both of these. And try to touch up that curve just a little bit.
Neatness points.
I know. Don't like losing those. Same thing, by the way, that I told you on the parabolas back in Algebra 2, is if you need to lightly trace with the pencil, you just kind of real lightly trace what you want it to look like, and then go through and trace more darkly once you've got it actually traced over, and you can get a nice, neater curve that way as well. Kind of like you do with these posters, right? I'll trace it all in pencil really lightly first. Once I've got that all traced, then I'll go back over with the Sharpie and erase any extra pencil marks. But that way I can make sure it looks really nice before I make it. Questions on this? Questions? Well, they don't get printed. I mean, if I want it, I got to make it. So people don't make math posters enough.
How do you draw that neat, write that neat?
I worked really hard at it when I was in high school, or really more elementary. But yeah, I guess a little in college too. They had us practice our penmanship in college as part of our teaching training.
So like all of this, how long did these take you to make? Like days?
I don't know. This was years ago. I made most of these. Some of these are newer. But most of these are really old. All right, questions on this? Questions on this? I feel like we got the amplitude change. You're going to practice a little bit with that in your homework. One other change we're going to talk about, next thing in your notes, inversion. Inversion. Now, you'll remember from geometry last year about an inversion transformation. Sound familiar? And the inversion transformation of proportion was when you did what to the ratios?
Inverted it.
What does that mean?
Reciprocal. Flipped it.
Flipped it. That's the word I was looking for. Flip it. Inversion means you flip the graph. Inversion. Flip the graph. How will we know that we need to invert? Well, technically, when I write f of x equals a sine x, there's an understood sign, S-I-G-N, in front of it all. An understood positive. But you understand, a negative would take any positive values and shift them down to negative. And any negative values and shift them up to positive, right? So if there's a negative sign, that tells me to invert. A negative sign would tell me to invert. A positive sign means leave it like we've been doing it. We've been working with these understood positives, but an inversion is going to flip the graph. And just like we want to change everything with the amplitude based on key points, we're going to invert based on key points as well. So let's take a look at a couple of these. If you'll set up another graph grid, you're going to be doing lots of graph grids over the next week and a half. All right, so let's set up another graph grid.
Is this material going to be on the exam?
Oh, yeah. I'm teaching it before the exam, so, yep. All right, so let's take just a basic function, f of x equals negative sine x. And I don't know why I randomly did a cursive f right there. Math doesn't use cursive. F of x equals negative sine x.
Is that a capital, is that a cursive N too?
I don't think so. Well, I was writing the I, so this is a better, and my chalk just happened to drag on the chalkboard there.
Mm-hmm.
Yeah. All right, so we've got our f of x axis and our x axis, and pi over 2, and pi, and 3 pi over 2. You know, if you were smart and you had one of those copier printer things at home, you draw one of these really nice and neat, put it down on that tray, and like run off a bazillion copies. Anyway, that's just a thought if you happen to have one of those fancy printers.
Laminate it and everything so you can just erase it.
Hey, there you go. Now we're cooking with gas. If you happen to have a laminator at home. But they make those laminating pouches, but I've seen people like for home use have those. You slide a paper into a laminating pouch and it seals it up. Anyway, so for f of x equals negative sine x, what are my normal key points for sine class?
0, 1, 0, negative 1, 0.
All right, those who are saying it out loud are going to really benefit and are going to remember this really well. Those who are not saying it out loud are not going to remember it as well.
All right, trying to be exact.
So when we flip it, all the signs are going to change. Well, you can't change the sign of a 0, right?
Right.
But you can change this to
Negative.
and this to
Positive.
There we go. That's going to flip the graph. So we're going to start at 0, and instead of going up to 1, we're going to go down to negative 1, back to 0. And instead of where we normally would be going down, now we're going up to 1 and then back to 0. But we have the same 0.9s, square root of 3 over 2, on either side of the 1s. We have the same 0.5s, 1/2, on either side of the 0s. And we still connect with a smooth, continuous curve. That's mostly accurate. And there we go. It's the same curve we had before. It's just flipped. In fact, you know, I could draw what did it used to look like? Well, it used to look like that, and now it just got flipped over. Okay? And now it kind of looks like an infinity symbol. Questions on that? Questions? Let's do the same with the cosine. So go to another color of ink, or perhaps to a pencil if you were using pen if you were using pencil. This is that one time, you know, some girls like having a bazillion colors of pens in their purse for some reason. This is the one time, like, it's like, hey, this is a win for you. Normally, I'm like, who needs all those pens? But this graphing, it does
Stop being
help.
so quirky. Like,
I know. F of x equals negative cosine x. What are my key points of cosine normally?
1, 0, negative 1, negative 0, 1.
But if I'm going to invert the graph because of the negative,
Negative 1, 0,
1, 0, negative.
all right, so we're going to start down here at negative 1. go up to 0, up to 1, back down to 0, back down to -1. Of course, with the 0.9s by the 1s, and the halves, and we trace with a smooth, continuous curve, something-ish like that. And there's our inverted cosine curve. Again, it's just the same cosine curve we used to have, and it's flipped over. It kind of looks like the double helix DNA molecule or something.
Might as well just sit out the classroom.
Might as well just wait. She's gonna have to watch the whole video anyway. But it's good to see her smiling face. There's a smile. All right, hi Jamie. You're gonna have to watch most of this video later, but you know.
You mean all of it?
Pretty much. Hey, she's here for the last minute or two. All right.
To get the homework.
And she'll make up the quiz during you're at study hall. We'll eventually make up a quiz. All right. Questions on inverting the graph. All right. So write this down if you would on your paper, and let's put both thoughts together. Let's put inversion and amplitude together at the same time. So new graph grid. At this point, Jamie, I would just sit and watch rather than try to do this with us because you missed all the introductory material. But this way you'll at least see it the second time when you watch it on the video instead of for the first time. There's some benefit to it. All right. So set up your graph grid with your f of x axis and your x axis. 1, 2, 3. -1, -2, -3. Remember, every 2 boxes 1. And your pi over 2, and your pi, and your 3 pi over 2, and your 2 pi, again, every 3 boxes. And let's go ahead and graph f of x equals -3 halves cosine x. -3 halves cosine x. Now, which we're always going to start with, class, are key points. What are my normal key points for cosine?
0, 1, no, 1, 0, -1, 0, 1.
But I'm going to flip all of them,
-0, 0, positive 0.
and then we're going to multiply all of them by 3 halves.
3 halves.
-3 halves, 0, positive 3 halves, 0, -3 halves. Does that make sense? Which 3 halves is a fancy, weird way of saying 1.5, right? So we're going to start at -1.5, then to 0, positive 1.5, 0, -1.5. Normally, next to what would be 1's, class, we would have the 0.9s, right? We'd have the square root of 3 over 2 here. But we need to multiply that by 3 halves. So what is the square root of 3 over 2 times 3 halves on your calculator? Square root of 3 over 2 times 3 halves. It'd be 3 square root of 3 over 4, whatever that is. 1.29, okay? So that means right here we're going to be at, now here's 1, or -1, here's -1.5, -1.29 is going to be about halfway, right? So we're going to do the same thing up here. We're going to come about halfway down the box, and then here we're going to come about halfway up the box. And then, of course, we normally would have 1/2 next to the zeros. We're going to multiply that by 3 halves to get 3/4. Well, again, here's 0, here's a half, here's 1, so 3/4 is going to be right in between. So 3/4 for all of these, and then we just connect with a smooth, continuous curve, which is hard to see through my hand, and something, but only something, like that. Does that make sense? So you can put both amplitude and inversion together very easily. So I teach both in the same lesson. Questions on this? All right. What about, let's go, I'm going to change to a different color. Do likewise. Real quick as we finish out, f of x equals -3 sine x. F of x equals -3 sine x. All right? Normally, key points of sine.
0, 1, 0, -1, 0.
Let's do both changes at once. Let's invert and multiply by 3.
0, -3, 0, 3, 0.
Basically, you just multiply by negative 3, right?
I don't know how I can compete with that.
All right, so we're going to start at 0, go all the way down to negative 3. Back at pi, we're back to 0. 3 pi over 2, we're all the way up at positive 3, and then 2 pi back to 0. And for sake of time, what we're going to try to do is just draw the smooth continuous curve based on those key points. And it's not going to be perfectly accurate. I wouldn't do that on a quiz or test. I'd take time to figure the halves and the square root of 3 over 2's times the negative 3. But for sake of time, we're pretty close. That's a pretty accurate graph of the curve. Questions on this? Homework for this evening, you have two functions. Let me write it off to the side over here, so I'll slide the screen over as well. For homework, I want you to graph f of x equals 2 cosine x and f of x equals negative 1.5 sine x. Graph just those two functions for homework. You can do them on the same graph grid if you want, or if you really don't want, you could put them on separate graph grids, but I'm lazy, so I put them on the same one. All right. Have a wonderful rest of your day, and you are dismissed.